So now we're starting to go into alternating current and what those circuits are like. So first of all, when we're doing circuits with alternating currents, they use this symbol instead of the traditional DC, which, if I remember correctly, is like this with an voltage across it. So the first thing we're going to talk about is when you're generating AC power. We already talked about how it comes naturally because if you create a generator with a coil being spun between the north and the south of a magnet, and you have this rotating motion going around this way, what you're going to have is you're going to be having flux that is going to be varying like a wave. It's going to be varying kind of like that. And so we've already talked about the math behind this, and when we worked it all out, the voltage that we found was 4BA all over T. Now T was the period, which it's basically the time it takes to take one full path through a wave. That would be T. And the period, if you remember, is 1 over the frequency. So if they give you hertz, you can figure out the period very easily. So this B right here is the number of Teslas, and then this is the area of the coil that you're rotating in the magnetic field. So one example I'm stealing from the book is, let's say that we create a generator with a frequency of 60 hertz. And like we've talked about in class, that is the natural frequency that we get in our houses. That's the frequency we get for our alternating current in our normal everyday life. We're going to say that the magnetic field is 1 Tesla, and we're going to have a massive coil. We're going to have something like 5 meters squared of coil, and let's just estimate kind of what the voltage generator would be. So the absolute value there is just kind of a nicety. Basically, we're just going to be doing 4 times 1 times 5 all divided by the period. Now back up here I said that the period is actually 1 over the frequency, and they're giving us the frequency, so we can write this as 1 over 60 hertz. Now that is actually the same as if we take 4 times 1 times 5 and then times by 60 over 1. You take the fraction. You keep the top, you multiply by the reciprocal of the bottom. And then when you crunch all this, you get about 1200 volts. Okay, so generators typically create hundreds and thousands of volts. And the wires carrying current to your house have tons of voltage in it. And then it's stepped down using transformers. So when it actually gets to your house, it's been reduced down to the voltage that we know, which would be about 120 volts. So we just want to talk about a little bit about this harmonic motion. What you saw up there is already harmonic motion. Basically anything that moves in a sine wave like that or a cosine wave is harmonic motion. So a spring, if you were to put a weight on a spring and pull it down and let it release, it would naturally go up and down in a wave motion. And so when you have an AC current and a resistor like this, this is the simplest type of, I guess, AC circuit. What you're going to see is you're going to see that the voltage, and this will represent the voltage here, alternates like so. And when we talked about sine and cosine waves, the amplitude was always the thing right in front of the equation. And these amplitudes are going to be, we'll call it V max and then negative V max. And what I mean by in front of the equation is that we always wrote a sine of 2 pi f t. So this V max is going to be your amplitude. What I'm getting at is that in an AC current, the voltage is always changing. In a DC current, you have a constant, theoretically a constant voltage that is always there. And so there's a difference between, or I should say that depending on the time, the voltage actually varies between the positive maximum and the negative maximum. And so if you want the instant voltage, this is the equation to find it. Now if I give you a certain amount of seconds of frequency and the maximum voltage that this wave goes through, you'd be able to figure out the exact voltage at that point. So, I don't know, maybe after 2 seconds you are right here on the wave, which would be slightly higher than the negative max, but it's not exactly the negative max. So, as time changes, here is the formula to figure out the voltage. Now, along with this is the actual current. Current runs along with your voltage. But remember that current is the same as voltage over resistance? Well, we're going to use that here, except we're going to just substitute this instead of a regular V for DC. If you divide by R, this would give you an exact current with a certain frequency at a certain time if you know all these variables. Instead of the general current that you would always get on DC, this will tell you the current as it changes with time. And so, by the way, current actually changes with your voltage. And so current is going to look something like this if you were to graph them right on top of each other. They're going to have the same highs and lows, but they're going to be in sync. They are in phase with each other.